Having looked at the intuition and some cases around jump search, let's get on writing a function that does jump search for us. Like I said, this has to be done a little bit carefully. So I get back to my Colab notebook and I just write like a title here, jump search, say function. And for moving forward, I just create a code cell, and here I'm going to write my jump search function. So I just define a function called say jump search. um, you know so three arguments: one L, the list in which we are searching; X, which is the value that we are searching for; and an M, which is my jump step. So let me just write a small little comment here: jump search for X in L. Jump size is M, right? So now remember, the way we are going to do this is basically jump search requires two passes. The first pass is the searching of the jump locations, and then the second pass, if needed, a linear search in that subrange. So we've identified five cases. Let's see how all that comes together. I'm just going to define a few variables. N is, let's say, length of L, so that's the total number of arguments, total number of items in this list. I define a variable called index, IDX is 0, and I use a Boolean variable called overshot to keep track of whether or not I have, you know, um, overshot, I've gone ahead, more than the value that I was looking for. And this will happen in the first pass. When I go the jumps, it's quite likely, because data is sorted, if I make a large jump, quite likely that I might just overshoot, and in which case I'll have to come back and do a binary search. So now I'm going to write this basically like a while loop. So the first pass, basically I just go and say while not overshot. Remember, while condition, while loop works while this condition is true. I've set overshot to false, so I say while not overshot and IDX less than n, right? So now both are important. Basically IDX is like a pointer. I'm going through that list. I must make sure I don't go beyond the list, because that will immediately cause an error in my let's say in the code, right? So I just go and say both these conditions have to be correct. Remember, case one was when I found the item on the jump locations. That's like a, basically it means the item is there and I don't need to go further. So I can just go and say if, let's say, L IDX is equal to say X. So I have found the item. Let's just say item found. And for the sake of reference, so I just put say case one. Now remember, on the jump location. So basically this is a situation where, as I jump through the list, I find that, okay, the item was found right there. And if that is the case, I can return index, and really that's all. So I basically pretty much the loop has to end right there, right? Because sorry, not X, but in fact index, because that's it, right? There's nothing more to be done. We can just return from the function. On the other hand, let's say I find that, look, I haven't found the number that I was looking for, but I've had a situation where L index has become more than X. So what does this mean? It means that I have overshot, right? So I have overshot, and now this could happen in many situations. Maybe the number is part of the list, maybe the number is not part of the list, but in either case I have overshot, which means that I have to now, let's say, go back to the previous jump, to the previous jump location, and we will take care of this. I must anyway get out of the while loop, which means that I'm going to set overshot to say true, because clearly I have overshot from here. I must now, go back to the I'm clearly overshot. However, remember, if my index were 0, so if at the very first location, if this overshoot happens, well, that is basically case 5. So what does it mean? I search item smaller than the smallest. So this is basically my case 5. Like I said, this could have been solved a little bit more trivially. Even before getting into while loop, we could have done a comparison and solved it, but we are doing it as part of the unified algorithm, let's say, so which is also fine. In this case, item is not in the list. I just go and return say -1. On the other hand, if let's say none of these, so be careful with the indentations. This is a situation where I have overshot. If I have not overshot and if I have not found the value, remember, if else, I'm getting into only one of the three conditions, one of these conditions. So if I find the value, well and good, I just return immediately. If I on the other hand overshoot, then I know that I've overshot. I have to exit the loop. I must get into linear search. I just do a quick check if I'm overshooting at the very first level or not, right? If none of this happens, right, I must basically just continue my jumping process, in which case I'm just going to say index is equal to idx plus m. Of course, I can write this more concisely by saying plus equal to m. Yeah. So really, let's just sort of think about what's going on here. So back to, let's say, this diagram here, in case one, I'm jumping through this list. So I found the element, I exit. That's my case number one. Case number two, I have overshot, but still I'm jumping here. I overshot, I've come back. Same story with case number three. I do not know yet if the item is in the list or not in the list, but I have overshot. I'm going to get into second pass. Case number four is similar. Basically, I've gone all the way to the end of the list, and I have the last case that we have covered is case number five, which is the case where I overshot at the very first instance, right? In which case, I know that the value is smaller and I must get out of the loop, right? In fact, I can return -1 and that's the end of the story. Now, if none of this has happened, basically, I'm going to keep going for further and further. But remember, I must stop. My case 4 has to happen. I must stop if my index becomes more than n, because if that were to happen, clearly I can't go further, right? So the situation will be, look, I jump, just keep jumping, my index goes somewhere here. Now the moment this happens, I will have to clearly get out of the loop, and that is where the second part of the while loop comes in. The second condition on, let's say, the while loop comes in, which is basically index less than n. So both of these have to be true. While not overshot and index less than n, I will keep doing this. The moment I do overshoot, I either overshoot or I go beyond n, I will in fact terminate the loop. But mind you, at that point, assuming I'm not overshot, right, my index is in fact more than the list value. If I've overshot also, I must come back to the earlier point, which means that outside of the while loop, now be very, very careful of the indentations here. Outside of the while loop, which is aligned with this statement here, outside the while loop, I will go and do idx equals to idx minus m. So which means that it is just say, well, go back to the previous jump, right? So go back to the previous jump location. Now think through it very carefully. The moment I go back here, in fact, all I'm going to do is to start a linear search, because this is now I'm either in case 2, case 3, or case 4. Either case, I have to do a linear search. And we have seen code for linear search. What I can do is to say, okay, for kk in range, say m, I basically, remember, I'm at the previous jump location right now. I will just ask myself a question. Okay, look, if say kk plus idx, so I'm basically increment, let's put it idx plus kk. So remember, idx is my pointer. If I were to look at idx plus kk, if that were to become more than n minus 1, well, this is case number 4, where item larger, so say search item larger than the largest. If this is the situation, clearly I must return. Now again, like I mentioned earlier, this could have been checked trivially upfront, but never mind, this is also fine, right? On the other hand, if I find that, look, I'm not at the end of the list, which means that's okay, I can keep searching. However, if I find that my, if let's say l idx plus kk is equal to, let's say, x, so which means that, look, I did find this item, I will return, for example, idx plus kk. Yeah. Now assuming none of these conditions happen, which means I am very well in the list, but I don't find this item at all, the for loop runs its course, I will get out of the for loop, and from here I can return, let's say, a -1. So this is a situation when item, let's say, search item not found. So this is would be, in our case, case 3. So it's in the range, but it's not found, and hence I am basically coming here, right? So think through this. Like I said, relate those cases that we discussed earlier, and see how the code is taking care of each of them. And this is a good exercise, right? Logically think through this. It'll be very interesting to, let's say, analyze. One thing I must highlight is that there are further opportunities to, let's say, make this gain incremental efficiency. There are a few places I'll highlight. Number one, for example, when I do a linear search, right? I mean, the second pass, notice I'm going back to the jump location. In fact, I could go here instead of going from, let's say, all the way from 0 until m minus 1. What I could do is to go from 1 until m minus 1 because the jump location has been already searched, right? So that is correct, because if this is basically, this is kind of a little bit repetitive. I can in fact go and say 1 m in steps of 1, right? So remember, this will be going from 1 all the way to m minus 1 in step of 1. Remember, because m itself will not be covered, which is fine, right? Now, the second optimization we could make is that, look, I could terminate the loop right away if I find that L idx plus kk is more than x, right? So in which case I could return minus 1, but that's okay, not too much. Yeah, maybe I run a few more extra comparisons in the linear search. So there is a little bit of incremental efficiency to be gained for case number 3. I mean, happy to explore. Definitely think about it. But I hope this picture is clear. Once again, relate back to these. Relate back to these cases. Go through the code carefully. Very, very happy to discuss with you in case there's any confusion, and also explore your own optimizations. I kind of alluded to a few of them, but there may be more, ways to write this code. Happy to look at your code, the way you want to do this. But obviously, remember, correctness is important, and that's cannot be compromised. I hope you found this interesting. Look at our website www.ybyte.in for more such content. In our algorithms and Olympiad track, we are analyzing algorithms in a fun, lively manner, easy to understand. Look at it, and happy to discuss. Enjoy programming. Thank you so much. Take care.